I am Jagadeesh. I'm a student at Department of Electronic Systems Engineering. Today I will be presenting my project titled Time Synchronization in Networks. This project was carried out under the guidance of Professor Chandramanasi. Time synchronization is the process of aligning clocks across devices in a network system by minimizing clock offset between them. It is essential for ensuring the devices in a network operate on a shared and accurate time reference to ensure coordination, consistency, and security, which finds applications that require sub-microsecond accuracy. To understand how time is distributed in the network, let's understand the protocol list. One of the earliest protocol used is NDP. This NDP protocol based on the client server model. The client will poll one or more NDP server for which are precise time sources. As shown in the figure, the client will try to poll NDP server to capture all the timestamp through the handshake from which part delay and time offset or offset are obtained using these expressions, which are used to adjust their local clocks accordingly. Since the timestamps are captured at the software level, the synchronization accuracy is limited to in the order of few milliseconds. Another protocol which is widely used in today's applications is PTP. The basic idea remains same as NTP, and the key difference is the timestamps are captured at the hardware level closest to physical network interface, which eliminates the software delay incurred and improves clock synchronization accuracy. While PTP requiring hardware timestamping, it uses software to manage timing adjustments and manage clock info. It calculates the mean for delay and time offset using the same equations as NTP. Coming to PTP roles, there's a client and server in NTP are renamed as master and or grandmaster and slave in PTP. In PTP extent, the grandmaster ensures the communication by sending sync message at regular intervals after the slave. The ordinary clock then sends the delay request to the grandmaster clock, and which is obtains a delay response T4 based on this timestamps. It will calculate the delay and offset and use it to adjust their clock. The two messages that are used in PTP are enhanced and signaling. Enhanced message is used to determine the best clock in the network using best message clock algorithm, and signaling messages are used to handle configuration queries and management. So having discussed two protocols, PTP and NDP, let's see why PTP is used most of the applications. I discussed PTP uses a hardware timestamping network interfaces which always a software delay. And PTP supports configurable synchronization intervals, all-in quick correction, and PTP uses the clock hierarchy like transferring clocks and boundary clocks, which are used in the network strategically to preserve the timing accuracy even across multi-hop complex networks, and like which something can NTP can handle. This is the PTP message format and fields. PTP message is encapsulated in the UDP payload with the header that so bytes and body of variable in. The PTP message header format is same for all the PTP messages, and each field in the PTP header format specifies key function, message type, specifies which message has been sent, and sequence file tracks the order of messages, and control field indicates the function or type of the message. PTP defines several types of clocks. Grandmaster clock acts as the primary time source in the PTP domain. Ordinary clocks as end host that requires synchronization, has only one port and acts as master or slave. Boundary clock has multiple ports which can act as master and slave. When talking to grandmaster, it acts as slave, and when talking to downmaster, it acts as master. Transferring clocks are used in between the master and slave nodes, which compensates for switch delay by updating PTP event messages. Something comes residence time, and when the PTP message passed through them. Let's see the before networking language and packet processing. P4 is a high-level language for programming data plane of network devices like switches and routers. It is protocol independent and enables programming pipelines like parsing and ingress and egress ports, transaction tables, and deparsing. Each hardware platform must provide its backend compiler to translate the P4 code into device executable logic. This is the figure showing the pipelines, how the packet is obtained with the input and passing onset stages, and what has to be action. Action has to be done in the ingress pipeline, and based on the forward rules, it has to be sent to the egress pipeline and sent to the destination. Coming to P4 platform, we have software and hardware performance. In software, BMV2 is the reference switch widely used for testing and debugging P4 programs. It is running user space and relies on standard OS network stack and DMN. Hardware platforms, we have programmable 6 FPGA SmartNICs, which support hardware timestamping in the 48 to 64-bit resolution. SDN has two types of functionality at the control plane and data plane, where the control plane and establish and manages backup processing policies like forwarding and header writes and header rewrites and device monitoring. It ensures scalability because data plane continues forwarding even if the control plane is restricted. It just put the rules while data plane acts on it, acts as the brain of the network. Data plane executes the high-speed packet processing based on control plane rules. A process modifying a forwards packet minimal latency, and the programmability enables the dynamic change to low-level packet processing on the device hardware itself, making devices flexible and adaptable. This is the boundary clock program that is running on metronome. Boundary clocks handle the data request locally in the network, preventing overload and the large-scale network. The slaves are not directly connected to grandmaster. For handshaking, it will connect to boundary clocks so that the overhead on the grandmaster will reduce and the jitter will be reduced. And the grandmaster at H1 and metronome boundary clock runs before program as the switch H S1 and the slave H2. The grandmaster ensures communication by sending follow and sync and follow messages. So the boundary clocks based on the rules and actions it has been written in the software before program. It acts as on the packets and sends the clone follow-up and to the delay request as the delay request to grandmaster, and after the delay response calculate the offset and correct the offset and send and adjust the timing header fields in the time in the messages and sends to H2 based on the timestamp. It will calculate the Linux PTP on H2, calculates the offset and tries to synchronize to H1. At H2, the local clock is adjusted based on the offset between boundary clock and grandmaster, which can vary due to network conditions. To avoid sudden jumps on the offset, a PI-based servo logic is implemented in B4 program that ensures the timestamps are sent to H2, keeping correction stable and within safe hardware limits. So in this figure, the blue line is the offset which is continuously reducing. We have seen the offset is changing drastically at sometimes. There is a sudden jumps and peaks where it changes to extreme condition. The PS servo logic ensures that it is maintained in the valid levels so that the metronome hardware is not overwhelmed by the corrections due to the extreme time corrections. The PA control equation for frequency adjustment is used as Kp into current offset is K into accumulated offset errors. So this is the boundary clock hardware setup we have been using. The P4 program is run on metronome, and the internet two ports are used as H1 and H2, where H1 provides the reference clock and H2 tries to synchronize to H1 based on the program that is running being run on P4 metronome. This is the Wireshark image showing PTP message capture at H1. H1 is sending the announce sync follow-up message to boundary clock where it gets a reply with delay request and uptime delay response based on the 4 times now it will calculate the offset. That offset is given to PI based logic to correct the offset and ensure the offset is maintained between the levels, and it is given to the H2 where it can calculate the master and offset and continuously tries to synchronize to H1. In conclusion, we implemented the PI servo offset servo for boundary clock and impedance modeling using B4 and microC. I demonstrated microsecond level accuracy within programmable switches. We know that data plane only support basic integer operations. It will not support the complex tasks and floating point operations. We have to do the complex calculations with the algorithms. For example, the division can be approximated with the right shifts in the power of negative powers of 2. Looking ahead, we are trying to verify algorithm performance multiple large scale and multi-switch topologies, adding dynamic graphical delay conditions, and also looking to offload some of the control plane tasks to data plane to ensure greater efficiency using smart and switches. Thank you.